Welcome to this explainer where we're going to completely demystify the laptop, taking a real inside-out anatomy tour to understand exactly what happens under your keyboard. Have you ever looked at your machine and just wondered how all those microscopic parts work together to let you browse, game, and create? Well, today we are breaking down the whole shebang, from the very first spark of electricity all the way out to the physical metal shell that holds it all together.
All right, let's look at our roadmap for today. We'll start with 1, waking up the machine, then move to 2, the brain and memory, check out 3, graphics and displays, and finish up with 4, the laptop body. Let's dive right in.
Section 1, Waking Up the Machine. Our very first stop is the motherboard. This is the central nervous system that connects absolutely everything inside your computer, and we're looking specifically at the crucial sequence of events that kicks off the exact moment you press that power button. To start us off, I want you to think about this for a second. Have you ever wondered how your machine magically retains the correct date, time, and custom hardware settings even after sitting completely dead in your backpack for weeks? It has literally no connection to the wall. Its main battery might be totally drained, yet when you plug it back in, the clock is perfectly accurate. How is that possible? Well, the answer is the CMOS battery. It's this tiny, super inexpensive lithium coin cell, usually a CR2032, that sits right there on the motherboard. This little powerhouse lasts anywhere from 2 to 10 years, and its sole job in life is to provide continuous power to the CMOS chip. Without it, every single time you turned on your laptop, your system would just revert right back to its factory default time, and your custom boot settings would be completely wiped out. And this brilliantly illustrates why the very first thing your computer does during startup, the hardware initialization, absolutely must be secure. When you press power, your machine runs what's called a power-on self-test, or POST, checking the RAM, the CPU, and the storage. There's a well-known saying in hardware security: if the machine cannot trust the first code it runs, every layer above it inherits that problem. Basically, if the firmware initializing your hardware is compromised by a bootkit or malware, your operating system doesn't stand a chance. Security has to start before Windows or Linux even loads. Which brings us to a really massive industry shift, moving away from the older rigid BIOS system to the modern Unified Extensible Firmware Interface, or UEFI for short. The legacy BIOS was kind of trapped in an old 16-bit design, blindly scanning the first sector of your hard drive, the master boot record, just hoping to find an operating system. UEFI, on the other hand, is a fully modern 32 or 64-bit architecture. It supports the guide partition table, which is what allows for our massive modern hard drives, and crucially, it features secure boot. This uses digital signatures to literally block untrusted malicious code from ever running during startup. What's really fascinating here is the step-by-step morning routine of a modern machine. Instead of scanning old disk sectors, a UEFI system cleanly powers up, reads boot entries directly from its own non-volatile memory, selects the trusted boot manager, and then seamlessly loads your operating system kernel into memory. It's an organized, highly secure, and lightning-fast handoff. Okay, moving right along to Section 2, the brain and memory. Let's see how the foundation we just talked about supports the core processing area, which basically functions as your laptop's digital workspace once that OS is finally loaded up. To make sense of all the technical jargon we constantly hear, think of it like an office. Your ultra-fast NVMe solid-state drive, that's your deep filing cabinet. It permanently holds your operating system, apps, and files. Then you have your RAM, like DDR4 or DDR5, which is your active disk space. It's the temporary, high-speed memory where your computer places the stuff it's currently working on. And the CPU? That's the actual worker sitting at the desk, executing instructions and moving data between the filing cabinet and the desk. So, naturally, the bigger the desk, meaning more RAM, the more apps you can have open at once without your worker getting totally overwhelmed. Now on to Section 3, graphics and displays. Moving outward from the brain, we need to look at how all that processed data is actually turned into visual information and physically shown to you. Your visual processing power is going to come from one of two places. You either have an integrated GPU, which is built directly into the CPU chip itself. These are fantastic for everyday office work, and they just sip battery power. Or you have a dedicated GPU. These are entirely separate, power-hungry chips with their own dedicated memory built by heavy hitters like NVIDIA or AMD. If you're doing intense creative rendering, 3D modeling, or high-end gaming, a dedicated GPU is absolutely a requirement. And if you're buying a laptop today, you're pretty much choosing between 3 physical display options. IPS is your most reliable all-rounder, giving you great viewing angles for office and design work. OLED, however, is a real game changer. It delivers stunning, true blacks with literally an infinite contrast ratio because it completely ditches the backlight. Each pixel lights itself. Then there's TN, which, yeah, sacrifices color and viewing angles, but it offers incredibly fast response times for budget-conscious gamers. But keep in mind, the panel type is just one piece of the puzzle. Your daily visual experience is heavily dictated by these hidden metrics. I mean, a 4K resolution sounds great, but if the brightness is only 250 nits, you won't be able to see a thing if you're sitting near a sunny window. You really want 400 or 500 nits for that. Similarly, a high color gamut like DCI-P3 is absolutely crucial for video editors who need color accuracy, while a 144 Hz refresh rate, or even up to 240 Hz, is what gives gamers that buttery smooth motion. Finally, Section 4, the laptop body. Let's explore the physical chassis, the armor that holds all of these super delicate components together and keeps them running optimally. Let's talk about the hard physics behind what your laptop is actually made of. Aerospace-grade carbon fiber offers incredible lightness with a density of just 1.5 to 1.8 grams per cubic centimeter. That makes it totally perfect for ultra-portable travel laptops. PC and ABS plastics are cheap, sure, but they have terrible thermal conductivity. Meanwhile, aluminum-magnesium alloys provide a massive spike in thermal conductivity. We're talking up to 180 watts per meter Kelvin. And that leads to a crucial point. A premium metal chassis isn't just designed to look sleek or feel nice and cold to the touch. It serves an active engineering purpose. It literally acts as a giant passive heatsink for that powerful CPU and GPU we just learned about. It pulls those thermal loads right away from the motherboard, allowing your chips to run faster for much longer without overheating. Designing this body requires a seriously delicate balance of physics. The chassis must be incredibly rigid. Why? Because if your laptop flexes when you pick it up with one hand, it can actually crack the microscopic solder joints connecting the chips to the motherboard. On top of that, a metal enclosure provides robust, natural shielding against electromagnetic interference, which keeps your Wi-Fi and Bluetooth signals nice and clean. Engineers even have to calculate thermal expansion rates. They have to make sure that as the laptop gets